Hi everyone, here's the first of a couple small lectures on finite fields. So this is section 15.7 in the book. Now we've all seen a bunch of finite fields already. We could take Z mod if P is a prime, Z mod PZ. This finite field is so important we write it like this frequently. I haven't been doing that. It's very common. There's only one field with P elements. That's called F sub P, and is of course just Z mod PZ. And of course we've seen we can make some other finite fields. If f of x in maybe fpx has degree n, maybe bigger than 0, then fpx mod f of x has p to the n elements. I think we did this on a previous worksheet. But let's just think through it. I mean, the elements in here can be written uniquely as a0 plus a1, maybe a0 bar plus a1, x bar to the 1 plus dot 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 plus an minus 1 x to the n minus 1. And these ai's are just numbers between 0 and p minus 1. And so you can see we have p choices here, all the way through p choices there. We make p choices n times, and so that's how we get p to the n elements. Okay. All right, so here's, we're going to prove several theorems about finite fields, but the first is the following. If K is a finite field with p to the e elements, e is going to be an exponent, good letter for exponent, then every element of K is a root of x to the p to the e minus x. That's kind of crazy when you first think about it. It means there's this polynomial that all the elements are a root of, and it doesn't really even have to do much with K except in terms of the number of elements in it. Okay, so let's give a proof of this, and then we'll give some consequences. The proof goes as follows. K minus 0, because K is a field, we have inverses. So this K minus 0 is a group, in fact, an abelian group, under multiplication. Okay, so this is an abelian group under multiplication. The order of this abelian group is, well, p to the e elements of K, we took away 1 through p to the e minus 1. So if alpha is in our group K minus 0, then by Lagrange's theorem, alpha to the order of that group, p to the e minus 1, is the identity. That's 1. Okay. Okay. Then, all right, just multiplying both sides by alpha and subtracting, then alpha to the p to the e minus alpha equals 0. So alpha is a root of x to the p to the e minus x. That handles all the elements in K minus 0. Note, 0 is also a root. Just plug in 0, you get 0 minus 0. And so we've found that every element of K is a root. Now, there's a couple things that we immediately get to say from this. So remark, x to the p to the e minus x. Okay, there are p to the e different elements in k, and each one of those is a root. So this is certainly going to be divisible by x minus alpha, alpha in k. So x to the p to the e minus x is divisible by this one, but they're the same degree. So if I have two polynomials, one that divides the other in the same degree, this one's also degree p to the e, because I'm just multiplying p to the e different linear terms. These two polynomials are equal. Okay? So x to the p to the e minus x has no multiple roots. And that'll be important for us in just a second. I want to point out that there's another way we can see that x to the p to the e minus x has no multiple roots, say in kx. Remember back in homework 2, we said that a polynomial had no multiple roots if and only if it itself and its derivative were had no common factors. All right, so this is so important, the fact that it's no multiple roots. Let's prove it using that characterization too. Note d dx of x to the p to the e minus x. Okay, remember we're taking formal derivatives like in that earlier worksheet. And so this is equal to p to the e, x to the p to the e minus 1, minus 1. But here's something crazy that happens. Because we're working in an extension of fp, p is 0. So that means p to the e is also 0. And so this is just equal to minus 1. So since negative 1 and, well, pretty much anything, x to the e, p to, are relatively prime, I have no common factors, x to the p to the e minus x has no multiple roots. Okay, that's the end of this first video. Next video, we're going to take a look at the group structure of k minus 0. All right, see you soon.